As Nazi Germany and Britain dueled for air superiority, aircraft designers rushed to get their fledgling jet fighters operational. The RAF's Gloucester Meteor became the world's first jet to go into service in July 1944, the same month that the Messerschmitt Me-262 was just beginning its trials.
The 262 looked like a deadly shark. To me, it exuded power. The engines looked quite big, underslung on the wings, and you looked at the nose, which was very sharp, with 4 30mm cannon, and you knew this is a deadly punch. And altogether, if you wanted to use one word to describe the aircraft, I would say lethal. At that time, the top Allied aircraft, performance-wise, had a top speed of 446 miles an hour, and when I tested the Me-262 at Farnborough, we had a top speed of 568 miles an hour, 125 miles an hour faster than the fastest Allied fighter.
The Messerschmitt Me-262 revealed the future of aerial warfare, in which high-speed jet fighters would dominate the skies. Although very quick, the 262 could not fly supersonic, but the race to fly fastest was on. Early in 1943, the RAF received an alarming intelligence report. A German prisoner disclosed that work had started on a new aircraft with a top speed of an incredible 1,000 miles an hour, faster than the speed of sound. To counter this supersonic threat, the government turned to Frank Whittle, a visionary inventor serving in the RAF, and the designer of Britain's first jet engine.
Frank, like so many geniuses, he had a fixation of what he was after, and that was to achieve ascendancy for Britain in jet flight. He felt, and quite rightly so, that he was the right man to lead it along this path.
When Father was a cadet at Cranwell College, he began to think about alternatives to the piston engine and propeller combination. So whilst he was still a cadet there, he wrote his final thesis at the end of the 4th term and entitled it Future Developments in Aircraft Design. And in this thesis, he recommended the turbine as a potential prime mover for aero propulsion, which was pretty far thinking for a young fella. And then suddenly the penny dropped, as he used to say, around October 1929, and he realized jet propulsion. And so he then went through the process of doing all the calculations and even getting round to the scantlings of a proposed engine. So that's how his thinking was going, to rid aviation of the piston engine with its altitude limitations and the propeller with its speed limitations.
Well, we were, of course, doing our transonic testing on piston-engined aircraft. And in April 1944, we took the Spitfire up to the highest Mach number ever achieved with a piston-engined aircraft, Mach 0.92. And the aircraft was virtually destroyed on the pull-out from this, and the pilot was very lucky to escape with his life. And we realized we were at the end of the road, frankly, because a piston-engine aircraft will never achieve supersonic speed because of the drag of the propeller. Now, just as that road seemed closed to us, right on cue, the new vista opened with the jet engine.
The Me-262 had demonstrated that German aviation probably had the capability to develop even faster aircraft. The British intelligence report of a 1,000-mile-an-hour Nazi jet fighter gave Whittle the opportunity to demonstrate his prowess in jet engine design.
There's a lovely painting of the first engine called the Whittle unit when it was first started up on the 12th of April 1937. It shows him standing by the engine, which had accelerated away out of control when they first tried to start it. But it stopped at 8,000 RPM approximately, and then the engine faded away and stopped, and everybody heaved a sigh of relief. Well, the only person left standing by the airplane was Frank Whittle, because everybody else had fled. And people asked him why he didn't run away, and although he used to say, well, he was rooted to the spot by fear, I think really it was his baby, and he just couldn't leave it. And so he did stand with it until it decelerated and everybody came back.
Frank Whittle's revolutionary jet engine, the W2700, would need enough thrust to punch a plane through the sound barrier. It would be the power plant of a British supersonic aircraft whose goal was to reach a speed of 1,000 miles per hour. The aeroplane was the M52.
Top there. No idea what that is. Looks like a toast rack.
The company chosen by the Ministry of Aircraft Production to build the supersonic jet was the Miles Aircraft Company. Jeremy Miles was a small boy when his father's firm got the contract.
Presumably that's why they changed that.
Yeah.
That is interesting.
Yeah, quite an early stage.
It is an odd choice to choose a company which had a reputation for making small wooden aeroplanes to develop and build the first supersonic project. But bear in mind that the company, Miles Aircraft, had a reputation for most innovative prototypes. Their background was in racing and in making high-speed trainers.
They were very, very advanced thinkers, there's no doubt about it. No other aircraft company in the country was anything like them. A lot of them were still building biplanes right up to the beginning of the war. Miles had stopped building biplanes in the 1920s.
People were very appreciative of the fact that Miles had this wonderful innovatory streak in them, and that they might come up trumps with something.
At the time, very little was known about supersonic flight. Building an aircraft that could break the sound barrier would require a complete rethink of aircraft design. Leading the team facing this extraordinary challenge was a 25-year-old aerodynamicist named Dennis Bancroft.
Well, it all started on the 9th of October 1943, when F.G. Miles was called up to the ministry and presented with a small piece of paper like this, which says, would he like to, or could he design and produce an aeroplane, another research aeroplane for the ministry. And it was rather odd aircraft. The first requirement is that it should fly at 1,000 miles an hour. And another major requirement is, on this piece of paper, that it shall be flying in 9 months.
9 months?
Well, 9 months is impossible, obviously.
The Miles brothers would never turn down anything. A challenge to them was their way of life. And they seized on it, and their attitude was, well, we'll do our damnedest to achieve it.
Towards the late 30s, my uncle George joined the firm and progressively took over design responsibility for my father, who then was concentrating on the management of the rapidly growing factory. By the time the M52 came along, George was chief designer, and Dennis Bancroft was the leading light on the design of the M52.
All the aircraft industry that knew anything about aeroplanes thought that the supersonic barrier was impenetrable with modern aircraft.
In 1944, Britain and Germany were in a secret race to build faster planes. With speed came air superiority. The victor would control the skies. Dennis began his quest to go supersonic by looking at the one object that flew faster than the speed of sound, a bullet. In the 19th century, the speed of sound had been recorded during experiments with bullets. In recognition of the Austrian experimenter Ernst Mach, the speed of sound was designated Mach 1, 660 miles an hour at altitude, or 760 miles per hour at sea level.
But of course, a bullet goes from high supersonic speed down through to normal, whereas an aircraft goes from normal up through to so they were going in the opposite direction, which made a complication.
British ballistic researchers advised Dennis that drag could increase by up to 4 times as the aircraft moved from Mach 0.9 to Mach 1.1. On the only surviving blueprint of the M52, Jeremy Miles discovers how Dennis was modifying the frontal area of the fuselage to reduce drag.
That's interesting. There's signs of a sketch there overlaid on the drawing, more to the bullet shape.
That's
on
right.
which they had based a lot of the aerodynamics of the aeroplane. That's interesting.
Yeah.
Yes, it's obvious that the air intake hasn't been fully developed at this stage, understandably, because it's an early drawing, because in transonic and supersonic flight, they're going to have to make variable intake so that the airflow can be controlled according to the needs of the engine, regardless of what speed you're doing. It's going to be quite complicated.
In his campaign to keep drag down, Dennis now turned his attention to the wings of the M52. Dennis took the wing of a Spitfire as his starting point. He worked out that halving the thickness of a Spitfire's wing would quarter the drag. He reduced the drag by half again by giving the wing razor-sharp leading and trailing edges. Finally, by reducing the wing area of a Spitfire by 50%, he was able to cut down drag by half again. In less than a month, Dennis and his team were ready to present their plan to the men from the Ministry of Aircraft Production.
We gave them a GA drawing of our proposed aircraft with its specification of the size and dimensions and performance and all the rest of it, and said, this is what we suggest. We can meet basically your requirement of, we think, of travelling at 1,000 miles an hour. We did say that it was necessary. One thing was that we'd have to use a biconvex wing, and there was absolutely no low-speed information about a biconvex wing as whether how it could fly. So we'd actually made and tested a biconvex wing, and put it in our wind tunnel, and the figures we got from it at the lower speed of 200 miles an hour or so showed that it looked quite promising.
In December 1943, the Ministry awarded Miles Aircraft a £100,000 contract to build the top-secret aircraft. Work on a full-scale mock-up began immediately. To test the biconvex wings, Dennis installed them on a Miles Falcon aircraft. On the shop floor, the wings' sharp leading and trailing edges were an occupational hazard.
People were cutting themselves by pushing the aeroplane around.
That's why it was known as the Gillette Falcon.
Yeah, it really cut people out.
It was so thin.
Flight tests with the specially modified Miles Falcon would reveal if the ultra-thin wings would perform safely at low landing and takeoff speeds. The results demonstrated that the M52 would be able to operate with biconvex wings. In its brief, the Ministry had specified that the M52 must have an all-moving horizontal stabilizer. From transonic tests with the Spitfire, it was discovered that an all-moving tail is essential for a pilot to maintain control when he approached the speed of sound at Mach 0.83.
They were doing dive tests on the Spitfire and finding out that when you got over about 0.83 on a Spitfire, the elevator failed to work properly, and the aircraft just got in a dive and got out of control.
In other words, you're in a dive and the aircraft is trying to go more and more nose down. The only way you can counteract it is full-blooded physical pull on the stick. Since we reached the limits, there was either we couldn't do much about the physical strength aspect, so the thing to do was improve the effectiveness of the elevator. And we moved from the standard tailplane and elevator onto the all-moving tailplane.
In subsonic flight, moving the elevator produces a change in lift, which tilts the nose up or down. At transonic speeds, the nose and leading edges produce shock waves. Turbulence and buffeting disturbs the air travelling over the stabilizer, rendering the elevator useless. But with an all-moving tailplane, the complete horizontal stabilizer moves, and the surface is large enough to deflect the airflow and enable the pilot to keep the nose up at transonic speeds.
And we put an all-moving biconvex tailplane on the Falcon and flew that one. And so the pilots could do all the tests, they could prove the aeroplane would take off and land and fly around and had good stalling, well, reasonably good stalling characteristics, nothing severe, and to prove that that was satisfactory.
Although not capable of accurately simulating performance at supersonic speeds, wind tunnel tests with a small-scale model of the M52 confirmed that Dennis's original layout was aerodynamically on the right track. Wind tunnel tests from a larger 1/6 scale model gave more reliable indications that his design had reduced the M52's drag to the point that it could fly supersonic. Dennis now believed that the 1,000 mile/hour target set by the ministry was squarely in his sights. Frank Whittle was also making progress on the M52's specially modified jet engine.
Given the desired thrust to punch a small aircraft like the M52 through the sound barrier to achieve about 1,000 miles an hour, it was calculated that they would need a thrust, I think, of around 7,000 pounds. And Frank Whittle, Dad, calculated that if he augmented the thrust of the W2700 engine by using an aft fan and afterburning, he could achieve a sufficient level of thrust for this small aircraft to get through the very high Mach drag factor to transit the speed of sound. This is the model of the W2700, which was the engine which was destined to be the power plant for the M52 project. The difference is this is just the straight W2700 engine without the thrust augmenters, the reheat system, which was going to extend the engine down the back. But the principle is the same. The air intake is down here at this end, where the air enters here and here behind, and enters a double-sided centrifugal compressor. The air is accelerated outwards into a diffuser here, where velocity is converted to pressure. Pressure is increased to about 4:1 into these, which are the combustion chambers. Fuel is introduced into the inner lining of the combustion chamber, and the air travels this way, expanding, and then it is directed through 180 degrees through the nozzle guide vanes and through the turbine blades, and then out through the exhaust, giving you jet propulsion.
A prototype of this engine powered the Gloucester Whittle, which made the first flight of a British jet-engined aircraft on May 15th, 1941. By chance, Eric Brown had diverted to RAF Cranwell due to poor weather and witnessed the jet's first flight.
Suddenly out popped an aeroplane with no propeller on it. And I'd never seen a jet airplane in my life, and I didn't really know anything about jet propulsion. And anyway, I watched this with great interest. And it eventually took off about 7 o'clock in the evening. And the screaming noise that it went off at, and I was absolutely intrigued by it. First thing that strikes you as a pilot flying a jet aircraft is the marvelous view you have. There's no big engine sticking out in front of you. Second thing is when you get in there, the total lack of vibration, which you have so much in piston-engine aircraft. And thirdly, the lack of noise. There may be a lot of noise outside, but you're sitting ahead of the jet engine and there's virtually no noise at all. So these were the three big impressions. I think the advent of the jet engine is probably the most significant event that has happened in aviation since the first flight of the Wright brothers.
Jack Whiting was an engineer with the team responsible for increasing the thrust of the Whittle engine to be used in the M52.
Jim Hodge, the designer of the No. 4 augmenter, showed me his calculations and proved beyond doubt that we would indeed achieve 1,000 miles per hour. I went through his calculations and I have to admit that I couldn't fault them. But at the same time, Frank Whittle did say, "I sometimes have a feeling myself, Jack, that we could choke, but I think we're on the right track."
Whittle was going to give us a jet engine which would be given a huge amount of excess thrust by having, for the first time after burning, sometimes it's called reheat, sometimes it's called augmentation. What it means is you are going to burn raw jet fuel in the jet pipe, and this will give a tremendous amount of excess thrust.
He seemed, when he was talking about it, that he felt confident he could achieve the desired thrust. But of course he wasn't in charge of the airframe, and the problems of the intake, where you've got to reduce the supersonic flow to subsonic at the point where it enters the compressor, that was a little bit of aerodynamics being handled by others, I would say.
Creating the variable air intake required by Whittle's engine and designing the airframe that would cocoon it was a major challenge for Dennis.
The engine itself is a complicated thing, but quite a lot of the engine itself is just a duct, a large duct of about 3'6" in diameter, and it's red hot on the outside and full of these high temperature gases, so you can't put a structural member through it, you can't put anything through the engine. Whittle decided that they wanted the engine as a complete unit to be fitted to the airframe, because you couldn't really get it and service the engine easily because of the airframe being surrounded. So we had to provide the airplane with a hole in the middle, 3'6" in diameter, the airplane was then put vertically upwards in a hangar, and the 18-foot odd engine was then dropped down from the top, down inside the engine while the aircraft was vertical, and screwed in place, and then the airplane turned up in its normal position.
With the engine filling up so much of the fuselage, there was not much room for fuel, nor the pilot.
It was necessary to have the smallest frontal area possible, so you couldn't really put the pilot anywhere else except right in front of the engine, because if you put it above or below or anything, it would increase the frontal area very considerably in the drag. The pilot needs about the same 4-foot diameter, roughly, 3'6", 4-foot diameter cockpit as a minimum, and you've then got to get air in as well, so you have to have a very small cone, which is obviously the only place is fitted at the front, so that's why he was at the front.
The minuscule cabin meant that Dennis needed to find a test pilot who was no more than 5'6" tall. Fortunately, one of Britain's best test pilots, who had earned the nickname Winkle for his diminutive stature, was short enough to squeeze into the M52's cockpit. But in the event of a critical emergency at supersonic speed, how would Eric Brown escape? Pulling back the canopy and bailing out was not an option at 1,000 miles per hour.
The whole nose of the M52 was an escape module. In the event of an emergency, the pilot could fire 4 explosive bolts, which would disconnect the nose from the fuselage and also project it forward, so it would escape from the main body of the aircraft. And it would then deploy a drogue which would slow up the nose to a speed at which the pilot could then bail out manually from the capsule.
In 1944, the United States became aware of the M52 Supersonic Project. The Bancrofts recall an official visit to the M52's secure assembly area by a small delegation of American aviation specialists, including a representative from the Bell Aircraft Company. The Americans were also given a demonstration flight of the Falcon, with its biconvex wings and all-flying tail.
We had been instructed to give every detail of the plane and of the project to the Americans, and the drawings, and answer all questions, and they were then going to have us going over there to get all their gen 3 weeks later. But lo and behold, that visit to America was immediately cancelled.
America said that
they said it was too top secret. They couldn't. Everybody thinks it's because they hadn't got anything to give.
Quite. When we talked to them, we found that they knew pretty well nothing about supersonic flight at all. And as Elizabeth says, we think they stopped us from going there because they had nothing there to show us.
Just when Dennis and the M52 team believed they were on the home straight for the first test flight, they learnt that Bell Aircraft had been given the task of building America's contender for the first plane to fly supersonic. The end of the war put the Germans out of the supersonic race. There was a rush amongst the Allies to capture their advanced aircraft designs. It was revealed that unlike the M52's straight wings, German aerodynamicists favoured swept-back wings for their high-speed aircraft. It also surfaced that the typist transcribing the intelligence report had accidentally substituted miles for kilometres. The German prisoner was describing an aircraft that could fly 1,000 kilometres per hour, not 1,000 miles an hour. Germany's DFS rocket-powered reconnaissance aircraft eventually achieved 900 kilometres an hour. Although unfinished at the end of the war, the prototype was taken to the Soviet Union, rebuilt, and achieved this speed. But on its third test flight, the aircraft suddenly stopped responding to the controls. The pilot successfully bailed out, using an escape capsule similar in concept to that of the M52. With Germany's demise, the United States was now the M52's main competitor in the race to break the sound barrier. The American Bell X-1 had moved quickly from blueprint to cutting metal. The X-1 was rolled out of the hangar ahead of its British rival in December 1945. However, Bell was forced to delay test flights for a year because of problems with the rocket engines.
There's no doubt about it. We were the foremost nation in the world. We were ahead of the Germans in transonic testing. And the Americans acknowledged this.
By early 1946, the M52 team were confident that they would win the race to go supersonic. But on the 13th of March, Dennis received a stunning blow.
When news of the cancellation was telephoned to F.G. Miles, I just don't think he could believe it. It just came completely out of the blue and as a total shock. Everybody was shocked.
Sadly, the M52 project was cancelled very abruptly, shortly before the prototype was due to be completed and to start its flight trials. The news apparently came out of the blue. My parents and everybody else working on the project were quite horrified. There were various reasons ostensibly given. One of which was that it was too dangerous to ask test pilots to risk their lives flying a supersonic aeroplane, which had never been done before. That, after all, is what test pilots do.
Without warning, the leading contender to break the sound barrier was scrapped by the Supersonic Committee of the Ministry of Supply and Aircraft Production.
We got a cancellation to stop all work, so all the labour was taken off it and put on other things, so that we just closed the doors and were told that we had to collect all the drawings and photographs and pieces and everything else and put it into this bay, and the ministry would then take it away.
At the time of the cancellation, Dennis had been confident that the M52's first test flight was imminent.
The first aircraft was a few weeks away from its first test flight, and the second aeroplane, the Supersonic, was mostly 6 or 9 months away. But we were so disgusted at that stage to cancel it, which we felt was a certain success, or a certain success, so close to completion. It was absolutely crazy.
Dennis and Elizabeth Bancroft suspect that secret British cooperation with the American X-1 project could have been a factor behind the cancellation.
Recently, I've come across an American report in the American archive that says that one of our directors entertained 2 American visitors to the aerodrome at Whittle, I think on the...
In July 46?
Yes, in July 1946, which was 6 months afterwards. And the real aeroplane, because they felt it and there was a sharp edge and they had to get underneath it.
And these 2 Americans reported back via their London intelligence headquarters to Wright Field in America.
About a year after the 2 American visitors inspected the M52 at the Miles factory, the Bell X-1 was delivered to Muroc Airfield in California.
It is quite obvious when you look at the X-1 that an awful lot of the information on our drawings has produced something that looks extraordinarily like an M52. Not in detail, because it had a rocket motor and it didn't have escape and things, but the shape.
Well, the Americans went for a rocket motor because they thought that they knew so little about jets. It would take years to develop a jet. They couldn't produce a jet. As it was a rocket, you couldn't take off and fly it because there wasn't enough fuel, so that you had to take it up with an aeroplane and just drop it, and then light the blue paper. And
so it wasn't really an aeroplane, it was a dropped body.
Yeah, flying rocket.
Dropped body.
Yeah, with wings.
Meow.
But the only useful information which they used, I think, was that we were designing and building a supersonic aeroplane, and we were convinced that it would work. And that just drove them on. As if we could do it, they could do it. So that's all they took away. But they didn't understand the rest of the technical information that they had in their briefcase.
In the autumn of 1947, the X-1 was ready to start test flights. The large dried-out lake bed in the Mojave Desert was a huge natural airstrip, and the only place in America where the X-1 could land safely. Test pilot Bob Hoover was assigned to fly the chase plane that supported the X-1.
Chuck was one of the few pilots I really respected and felt was highly qualified to do just about anything.
With each successive flight, Chuck Yeager gradually increased the X-1's speed. A B-29 bomber carried the X-1 aloft, as there was only enough fuel to light up the 4 volatile rockets for a few minutes.
The most critical thing he had was somebody above him cautioning him not to go any faster than some small amount of speed each time. He would have done it a lot sooner if they'd permitted him to do so. But he had to be really disciplined. I'm not sure I would have been that disciplined.
On the 10th of October 1947, Yeager took off on his 8th flight. The aim was to reach 94% of the speed of sound. After the X-1 was dropped from the B-29, Yeager approached the speed of sound. He was flying faster than anyone had flown before. Suddenly, he discovered that the X-1 would not respond to movements of the control yoke. The plane would not climb nor descend.
The sound barrier is a very, very positive thing. It really means that because an aircraft normally in normal flight sends a pressure wave ahead, which opens up the path for it through the air for it to progress. But as the speed of the aircraft increases and you get near the speed of sound, there is less warning given to cause the pressure waves to break up there, and they bank up on each other. So eventually you run into what, in effect, is a brick wall. And this causes changes in lift, huge amount of vibration, and a very big change in trim. If it runs away from you, you get into what the Americans so delightfully call a graveyard dive. And there is no way really back from that. The barrier is not just theoretical, it is very, very factual.
To stop the buffeting, Jaeger quickly turned off the engines and jettisoned the explosive rocket fuel. As the X-1 slowed down, the aircraft once again responded to movements of the stick. But if the flight control problems could not be solved, Jaeger would not be able to fly supersonic. The X-1's tail incorporated a feature to enable the pilot to adjust trim. So far, it had not been utilized in any of the test flights. When activated, it enabled the pilot to trim the aircraft by moving the entire horizontal stabilizer. It was, in effect, an all-moving tail. Bob Hoover recalls a crucial contribution made by Jack Ridley, another member of the X-1 team.
Chuck told him he was beginning to lose elevator control at high speeds. Jack came up with the idea of move the stabilizer up and down to give you more authority on the elevators and angle of attack, so it could hold the nose up. And when that happened, we knew Chuck had a real good chance of getting through it without any problems.
On his 9th flight on October 14, 1947, Jaeger wanted to find out if Jack Ridley's advice to use the trim switch would give him control at speeds approaching Mach 1. If moving the complete horizontal stabilizer still did not give Jaeger pitch control, the result could be fatal. Unlike the M52, there was no provision for pilot escape in the X-1. As Jaeger approached the speed of sound, the X-1 began to buck and pitch. He pushed the yoke forward. Would the all-moving stabilizer bring the X-1 back into level flight? Soon after losing sight of the X-1, the telemetry team heard a loud bang. It was the sound of the first sonic boom.
He went by me supersonic, and the reason I knew that, I was in a P-80, and it was an 8/10 Mach number airplane. Well, I remember it very well, very clearly, because I knew it was history being made.
As the needle went off the Mach meter, the buffeting stopped. Beyond the sound barrier, Jaeger discovered that air flowed smoothly over the X-1. Jaeger had reached Mach 1.06, 700 miles an hour at 14,000 feet, in a flight time of 14 minutes. The sound barrier had finally been broken. When the M52 team at Miles Aircraft heard that the all-moving stabilizer on the tail was crucial to the success of the X-1, they felt robbed.
Now, the flying tail is the fundamental innovation that the Americans got from us, and which was the thing that made the X-1 the first aircraft to break the sound barrier. Because the X-1 had run into an impassable stage in the tests at a Mach number of 0.94. And of course the flying tail is the one thing that will get you through the compressibility problems in any transonic flight.
But a year before work on the M52 started, some research on an all-flying tail had already taken place in the United States. Early in 1942, an all-moving tail was tested on a Curtiss XP-42 fighter to see if it improved control in high-speed dives. Up to now, no detailed engineering drawings of the M52, with its all-flying tail, had been found amongst the Bell X-1 project files. But recently, this rough sketch of the M52 was discovered in the archives of the Smithsonian Museum. It comes from the notebook of an American intelligence gatherer, Captain John J. Ide.
It's a very rough sketch, probably not more than about an inch or two across, giving brief details of span and weight and stuff like that. And it was dated August 1945, which is rather intriguing because we've got no record of any visits to Miles in August 1945. And we're wondering where he could have got that information from.
2 months earlier, an aerodynamicist working for the Navy by the name of Clark Millikan also visited the Miles factory. His report concluded that the M52 had little of use for US aircraft designers, and there was no need to obtain additional information from the British government. However, his report did state that the all-moving horizontal tail of the M52 might be of interest.
I've always thought that the Americans were behind the cancellation of the M52 in one way or another, either through pressure on a loan that we desperately needed, or through the fact that they wanted to be the first to break through the sound barrier. But having delved through records of governmental activities, through Hansard and the cabinet meetings, we could find absolutely nothing.
The government established a supersonic committee to monitor the M52 project, but it had no representative from Miles Aircraft.
There was no representation from Miles on it. In fact, it was 35 years before we even knew that they had a supersonic committee meeting every month. And they were just making decisions with actually wrong information. And the minutes of the meeting show that the information that they were talking about was completely wrong on many instances.
In 1944, Ben Lockspicer, the chairman of the Supersonic Committee, asked Barnes Wallis of Vickers Aircraft and Dambuster bouncing bomb fame to become a member.
Having got a foot in the door of the Supersonic Committee, he then very heavily influenced its thinking. And in my opinion, this could have been a severe setback in the progress of the M52 politically. And I think probably was quite a strong contributory factor to the eventual cancellation of the M52 as such.
Barnes Wallis believed a manned supersonic test aircraft would probably kill its pilot. He proposed a series of unmanned tests using scale models powered by rockets and launched from a Mosquito. The scale models would be built by his company Vickers.
A change, or a psychological change, had occurred to Barnes Wallis. The famous Dam Busters raid had cost quite a number of casualties, and this preyed on Barnes Wallis's conscience very heavily indeed. And he had openly stated that he would not now take part in anything that he thought would mean sending a young man out to his death as a pilot or aircrew. And therefore, he promoted on the Supersonic Committee the use of rocket models instead of a full-scale model of the M52. I think his concern about safety was genuine, but I think there was also a strong commercial interest running through all this. And we will never know eventually, of course, but at the end of the day, it had a devastating effect on the M52 as a piloted project.
For 7 years, we, the people of Britain, fought a war for mankind. Today we fight for our own survival. This battle we shall also win.
No doubt we're in a bit of a tough spot. And it'll take a year or two to get out. But we've done it before, and we can do it again.
So why did the government suddenly cancel the M52?
It is a bit of a mystery, but no government minister ever made a comment. It was a socialist government, a sort of in power, if that's the word at the time, that were absolutely dependent on foreign aid. They were absolutely bankrupt over the war.
In addition to saving test pilots' lives, the Supersonic Committee claimed that using rocket-powered models would save money.
No, that was a total red herring. I think at first it was put up as a money-saving project, but of course that did not prove to be the case. In fact, the contrary proved to be the case. Whereas the M52 would probably have cost about $250,000 to complete the project, the Barnes-Wallis project certainly was running into $400,000 to $500,000. So there was quite a difference.
Although Ben Loxposer, the chief scientist, has taken the blame for it all these years, we've discovered that he must have been the mouthpiece, and that the actual cancellation would have been ordered by his boss, which was John Wilmot, the Minister of Supply and Aircraft Production at the time, in order to make cutbacks purely on economic grounds, which turned out to be absolutely ridiculous, but that's the way it appears to have gone.
More than 60 years later, the cancellation of the project, when it was so close to succeeding, continues to irk the M52 team.
Livid, hopping mad, because to me it was utter betrayal. We were not given any prior warning of this decision. We were 82% complete for the first flight when it was cancelled. We had no tricky bits at that stage. The main components were all in place.
And it would have worked, and it would have actually flown, and it would have produced the information we wanted, and our frontline aircraft would have been that much better 2 or 3 years earlier.
I look at it as one of the worst decisions that ever happened in British aviation, because it happened at a critical time when we could have been the lead country.
The engine, the W2700, would have been an aft fan engine with reheat. Well, that in itself was a very advanced project, very advanced form of turbojet. It incorporated both turbofan ideas as well as the use of reheat. By cancelling that, which is really peculiar, the government simply turned their back on something which of course came along later, done by others. GE were the first to produce an aft fan engine in 1961. Frank Whittle was also working on a front fan axial compressor engine, the LR1, the long-range one, and he'd started work on that in 1943. So really it is a mystery as to why we threw the baby out with the bathwater when we cancelled the LR1 front turbofan and the W2700 aft turbofan. We put ourselves way onto the back burner.
He was angry, we were angry. We couldn't see the reason for it. But it took us some years to realise that it wasn't just technical. There was a lot of political angst in it as well.
The ministry's explanation never satisfied the M52 designers. The timing of the decision also made the M52 team suspicious. It occurred just 2 months after Frank Whittle resigned as chairman of Powerjets, the company that had developed the jet engine for the M52, and which had recently been nationalised by the government.
The government couldn't cope with Whittle, there's no doubt about that, and to have Miles on top of it, working together, probably they couldn't cope with that either, and it must have been very difficult for the powers. I don't know how they really thought they were going to cope with it, but Miles would have got the job done, there is no doubt about that.
And Whittle, who had been promised he could go on and develop new engines, was broken-hearted, of course, and he naturally became very difficult and fought madly for at least the compensation that would have enabled him to set up another private firm and compete on a legitimate level, but they weren't having that. And they threatened him with everything, loss of pension, being sacked, the works. And then, of course, I suppose some bright spark at the ministry came up with this idea about cancelling the plane so that Whittle could be quietly dropped.
I, as his son, can only say that he could be a bit fierce at times, and maybe he was a bit too fierce with some of these very self-important civilians in the ministry.
Whittle's ambitions for the future of power jets had been in conflict with the policy of the Ministry of Supply and Aircraft Production.
Frank's idea was that eventually his company should be able to produce jet engines as well as develop them. The Ministry of Supply begged to differ in this and said that no, that Rolls-Royce would do the production, but he would continue to do the development. And this upset Frank very much, to such an extent that he resigned as the chairman in December 1945 and left the company and took 16 of his top engineers with him. So this, to say the least, upset the Ministry of Supply, or it upset the establishment, if you want to put it that way. And to such a degree that one wonders why the cancellation of the M52 took place just a month later, or more than a month. It just took place in February 1946.
With its Whittle power plant, the fate of the M52 project was locked to that of the engine's inventor.
The sad conclusion that seems now to be accepted that it was cancelled as a rebuff to Sir Frank Whittle for, if you like, bucking the establishment. And one can hardly believe that a project that was going to bring so much prestige to British aviation and to the country as a whole could be cancelled just to rebuff one man. Not only sad, fantastically nasty.
In 1948, a year after Jaeger's historic flight, the M52 team had its bittersweet moment of glory. A scale model of the M52 made by Vickers broke the sound barrier. The test demonstrated that the M52 could have flown at 1,000 miles per hour, 1.5 times the speed of sound. Dennis Bancroft and the M52 team were vindicated.
The great expert on swept wings in pre-war was Professor Buseman of the research establishment at Focke-Wulf.
1944. A four-engined powerhouse flies through the clear skies over Kansas. The Boeing B-29 is ready to join the war after a lengthy and troubled development that began in late 1939. With 1250 caliber Browning machine guns and a standard loadout of 20,000 pounds of bombs, it truly lives up to its nickname, the Superfortress. Designed as a high-altitude daytime bomber, it is intended to be used in the Pacific theater of the war. The finished planes are flown from the Boeing plant in Wichita, Kansas, to the eastern tip of North America in Newfoundland, across the Atlantic Ocean to Morocco, to Iran in the Middle East, and finally to India, where they will be stationed for several months. From here, they can be sent to China, where they will be within striking distance of the home islands of Japan, which have been free from direct attacks since the Doolittle raid of 1942. But one of these bombers has a different fate. Its mission is not one of destruction, but of deception. It is flown from Kansas to Newfoundland and across the Atlantic. As its fellow B-29s are striking targets in Asia, first Bangkok's railroad shops, then the Imperial Iron and Steel Works of Japan, this one is headed for England. Instead of arriving under the cover of night, it arrives in broad daylight at RAF Bovington, northwest of London. Landing before a crowd of onlookers, it is driven up and down the runway, a show of the Allies' latest marvel of the air. And the crowds are impressed indeed. The B-29 is one of the largest aircraft ever built, at a length of 99 feet and a wingspan of 141 feet. But one of these onlookers isn't there to appreciate America's latest technological achievement. Returning home, the man is careful to conceal what he is about to do. Retrieving a straight key transmitter from a hidden location, he prepares to send a signal across the Channel to Europe. There, an operator receives the message and decodes the warning about this new threat, passing the valuable information on to the headquarters of the German Air Ministry. And this is exactly the scenario the Allies have been counting on. With good knowledge of where spies in England are located, it is known that this information will be sent on to their enemy. With the war dramatically turning against them, the notion of even heavier bombing is a frightening prospect for Germany. The US Air Force's Big Week offensive in late February of 1944 had the Americans flying heavily escorted bombing missions against airframe manufacturing and assembly plants around Germany. The results have been devastating, with the Luftwaffe losing close to 100 of their fighter pilots. Panic is rising all around, and this information is making matters much worse. The Americans have leaked enough information about the new bomber for the Germans to know just how much of a threat they are facing. If the B-29 is to be used in Europe, Germany will need to form a defensive strategy to shoot them down, and this poses a problem. The B-29, with its pressurized cabin, can fly at an incredible altitude of 40,000 feet. Though some of the German army's more powerful artillery can fire to that height, the bombers will be almost impossible to hit. And as Germany has not yet developed proximity fuses, it will prove a challenge for their defenses. If B-29s do appear in the skies over Germany, they need to be brought down by other methods. With the recent development of the turbojet engine, Germany now has fighter aircraft that can fly at incredible speeds. But will that be enough to combat the threat of the B-29? The Messerschmitt Me-262 is Germany's latest jet aircraft. Powered by two Junkers Umo 004 engines, it is a deadly adversary for Allied aircraft.
Right, now the Me-262 was, in my opinion, I've stated this many times, the most formidable aircraft of World War II. When you consider that at the end of the war, the top Allied fighter was the Spitfire Mark 14 with a top speed of 446 miles an hour. When we tested the Messerschmitt 262, it had a top speed of 568 miles an hour. This was a quantum jump in performance, and it meant the 262 was virtually inviolate.
Originally straight-winged, the production version of the 262 has wings swept at an angle of 18.5 degrees. This is done to adjust the aircraft's centre of gravity when the engine proved to be heavier than originally expected.
It had one shortcoming, but then I would say two shortcomings, but all the early jets did in our country, in America and in Germany. Firstly, the engines were very sensitive. They were slow to accelerate to throttle movement, and you had to handle them very carefully to avoid flaming them out. Secondly, we hadn't thought, or the designers hadn't thought, of how to slow down these incredibly fast airplanes, and no air brakes were fitted. And this made life very difficult, for example, for landing.
The 262's standard tactic against bomber formations approaching from a higher altitude and then diving down to their level and opening fire will not be effective against this new enemy. The 262 only holds enough fuel for approximately 1 hour in the air. It takes close to 15 minutes for the aircraft to reach its maximum altitude, not including the time it needs to locate its targets, which eats up plenty of fuel. Experiments are undertaken to see if this problem can be overcome. In one case, a rocket engine is added to a 262 to provide a boost during climbs. Another idea proposed to increase the plane's rate of climb is to mount ramjets on its wings. And while the ramjets will provide more thrust, their added weight would slow the aircraft down in level flight and deplete even more fuel. Tweaking the Me-262 is not the answer the Air Ministry is looking for. However, Germany also has a light fighter in development, the Heinkel 162. As raw materials and qualified pilots are becoming scarce, a cheap-to-produce and easy-to-replace plane is appealing. Officially named Volksjäger or People's Fighter, it is also known as the Salamander. Constructed primarily of wood, it is roughly half the weight of other fighters and houses a BMW 003 engine in a nacelle mounted on top of the fuselage.
The Heinkel 162 was certainly an intriguing idea. It was a well-designed aircraft. The catch is the Germans were running out of time. They were planning to use teenagers out of the Hitler Youth or out of the National Socialist Flying Corps, which at least had some basic training on gliders, train all these youngsters on gliders and put them on single-seat jet fighters, because there was no two-seat version of this thing, and hope for the best. Keeping in mind you had to produce these things. Again, you need the resources, you need the fuel, you need the workers. It was not an aircraft for the uninitiated. It was a jet aircraft, after all, a very high-performance machine. So put inexperienced pilots in a fairly hot machine with lots of Allied aircraft buzzing all around was not a good idea.
And despite its lightweight and high speed, the Salamander has even less endurance in the air than the Me-262, and so won't be able to combat the B-29 effectively. Several technical hurdles still need to be overcome before the next generation of German jet aircraft can take to the sky. In England, Frank Whittle's centrifugal jet engine has proved to be very reliable, able to endure over 100 hours of flying time before requiring repairs. But that reliability comes at the cost of speed. The Junkers and BMW axial flow engines, while much faster than anything the Allies have, are complicated to produce and last no longer than 12 hours in the air before a full retrofit is needed, and a total of only 25 hours until they need to be replaced. But new engine developments are on the way for Germany, courtesy of Heinkel He, the HES 011 turbojet engine. Featuring a unique combination of the axial and centrifugal compressors, it promises to be easier to produce and more reliable than the other German engines.
All German project development in the latter months of the war were all based around the HESO-11 engines. But then there were many other manufacturers, engine manufacturers, who were actually developing even more powerful engines. And some of today, modern day airliner engines today can actually be traced back to some of those ideas.
After the First World War, Germany had been forbidden from developing military aircraft technology. But they were not stopped from the development of all technologies related to flight. So while aircraft makers in the rest of the world were working to improve the performance of powered aircraft, the Germans were designing gliders, with many engineers taking a keen interest in aerodynamics and how to use the natural forces in the atmosphere to fly further and faster. The development of the modern wind tunnel by Ludwig Prandtl opened new horizons for the testing of how various shapes dealt with airflow. As war loomed once more, there arose a need for faster aircraft, and the proliferation of wind tunnels across Germany would help in the testing of new designs. So the development of the high-speed jet engine is identifying problems that had only been seen in wind tunnels before, that straight wings lose stability just above and below the speed of sound, in what is known as the transonic region. But in theory, a swept wing will lessen the drag caused by the formation of shock waves as airflow wraps around the wings.
The great expert on swept wings in pre-war was Professor Busemann of the research establishment at Focke-Wulf. And he gave an open forum lecture in Rome in 1935. And he put forward that sweeping the wings back doesn't mean you can go supersonic. What it does do is it smooths the transition from transonic flight to supersonic flight by reducing the compressibility effects. So it's a great aid on the way to supersonic flight, but it is not the key to supersonic flight.
Despite the fact that many leading aircraft experts of the day had attended the Volta conference in Rome and seen Adolf Busemann's presentation on swept wings, it was considered little more than an academic curiosity. As the airspeed record of 1935 had only been 440 miles per hour, the notion of supersonic flight seemed a very long way off. By the time World War II breaks out, Busemann's theories are all but forgotten. He conducts experimental wind tunnel tests of his theories, and by 1942 has amassed a considerable amount of technical data. Now, as planes on all sides are becoming faster and reaching the transonic region, they are witnessing the dangers that compressibility effects have on aircraft. Busemann's theories can finally come to the fore. Knowing that they have the technological advancements required to combat the B-29, Germany now needs an aircraft to house them. On July the 15th, 1944, just over a month after the D-Day landings, the Luftwaffe decides to halt all production of bombers and multi-role aircraft. Defense is now the name of the game. Calls go out to the top German aircraft manufacturers for an emergency fighter, a jet aircraft that can take on the threat posed by new Allied fighters and the American Superfortress. At Messerschmitt, preliminary plans for a new fighter are drawn up. This aircraft, designated P1101, will have a short, wide fuselage and tricycle landing gears. Willy Messerschmitt is curious about the benefit of swept wings, having researched the topic since 1940. Wind tunnel tests on models with various wing and fuselage profiles are conducted, and the differing results that each swept wing profile returns is intriguing. As many components have already been built, it is decided that the best way to get accurate test results is to build a prototype aircraft. Without the official backing of the German Air Ministry, Messerschmitt goes ahead and begins construction. It is given a mechanism that allows the wing sweep to be adjusted on the ground from 30 to 40 to 45 degrees. Other aircraft firms also submit designs for an emergency fighter. At Focke-Wulf, head designer Kurt Tank believes his team has some advantages over the competition. His FW-190 is already a workhorse for the Luftwaffe, with over 20,000 produced.
Kurt Tank was a brilliant designer, but he was also his company's assistant chief test pilot. And he had this huge advantage of knowing how to fly the airplane, and even was prepared to fly it in combat. When he flew from Bremen, whenever he was up, he would look around to see if there was any chance of getting a combat, and he was a remarkable man. He just thirsted for knowledge.
In March of 1943, one of Tank's team at Focke-Wulf had begun work on a series of design studies for a single-seat jet-engined aircraft. The man behind the designs is engineer Hans Multop. Multop had studied under Ludwig Prandtl at the University of Göttingen, where he wrote a thesis on the lift theory of wings. In 1938, Kurt Tank brought him to Focke-Wulf to work as his assistant in the Department of Developmental Aerodynamics, and by 1943, Multop had gone on to become a chief designer. Operating under the theory that the longer the distance the air must travel before it reaches the engine, the less power it will have, the Flitzer, or Madcap, is designed around a very short fuselage, with its jet intakes located at the wing roots. Its wings have a leading-edge sweep of 32 degrees. A twin boom holds the tailplane above and out of the way of the exhaust from its single HES-011 engine. The jet propulsion is to be supplemented with a Walters liquid propellant rocket engine, but it is removed from the final designs. Curiously, the Flitzer's design is very similar to that of the Vampire, another aircraft being developed in England around the same time. It is the second jet aircraft to be commissioned by the RAF. Both the Flitzer and the Vampire are single jet-engined aircraft with a short fuselage and twin booms supporting the tailplane. This coincidence comes about not through espionage, but simply the common logic of creating a jet fighter with a single engine for better fuel economy, and to provide centerline thrust. The Flitzer is well along in development, with a full-size mock-up and some prototype sub-assemblies completed. But despite the progress, the project is abandoned, because the plane's performance is expected to be no better than that of the Me-262. But when the emergency fighter program is announced, Hans Multop already has all the experience and knowledge gained from developing the Flitzer to work from. His next design, the TA-183 Huckebein, will be the culmination of aerodynamic research that his team began in 1942. And one of the major new steps implemented will be the use of fully swept wings. Taking its name from a mischievous cartoon raven, the Huckebein has wings mounted in the middle of its short fuselage and swept back at 40 degrees. It has a pressurized cockpit with a bubble canopy, providing excellent all-round vision. The Huckebein's fin is very long and tall, putting the tailplane above the flow of the air as it wraps around the wings, lessening the amount of turbulence. The first design uses a T-tail sitting at the end of a long vertical stabilizer swept back at an angle of 60 degrees. As tests progress, the T-tail gives way to a V-shape that is bent slightly upwards. It is intended that the plane will use the HES-011 jet engine. However, prototypes will use the same Junkers Umo 004 engine found in the Me-262. And like the Flitzer before it, early studies for the aircraft call for it to be equipped with a rocket engine, with enough fuel located in underwing drop tanks for a 200-second rocket burn. But again, the rocket engine is removed before designs move forward. A single jet engine will propel the Huckebein, giving it more range and better fuel economy than the two-engined Me-262. Expected to be able to fly at speeds of 1,000 kilometers per hour and up to an altitude of 45,000 feet, the Huckebein will swoop down from above and blast the bombers with its four 30mm cannons. But will cannons alone be enough? The B-29's revolutionary central fire control system allows the gunners to direct four remote-controlled turrets, each armed with two 50-caliber machine guns through the use of analog computers. Highly advanced for their time, the General Electric designed computers correct for airspeed, target speed, and other factors that can hinder the gunner's accuracy. These improvements make it dangerous for fighters to get too close to the B-29. To combat this, Germany needs an advanced weapon of their own. At the Ruhrstahl Company in Düsseldorf, Dr. Max Kramer is working on just such a weapon. His goal is to build a missile with enough range to allow it to be fired from well out of reach of the bomber's guns, while being guided with enough accuracy to hit its intended target.
During the Second World War, there was a lot of work being done on surface-to-air anti-aircraft missiles, guided weapons of various types. There was a bewildering variety of types that the Germans worked on. Not all of them very practical, mind you, but a lot of variety. They were also involved in early designs of air-to-air missiles. I know of one, which doesn't mean there were not more than one. I know of one, the X-4. Fairly small weapon, again, air-to-air. You wanted to use something that was tiny, just by Second World War standards, something you could almost hold in your arms. It is the ancestor of the modern air-to-air missile.
The X-4 is guided by signals sent via thin wires that run back to its guidance mechanism on the aircraft. As the missile flies, the wire is reeled out behind it. A small joystick in the plane's cockpit allows the pilot to guide the direction of the missile. That, as well as having enough rocket power to fly for 3.5 miles, makes it the ideal weapon for staying out of range of the B-29's guns. But because it is so difficult for the pilot to judge the distance to the target aircraft from so far back, the missile is armed with a newly developed acoustic-based proximity fuse, known as the Kranich. As the X-4 project is well known to aircraft engineers, the Huckebein is designed with the missile specifications and requirements in mind, possibly making it the first instance of a complete weapons system. On February the 28th, 1945, the Luftwaffe High Command examines the emergency fighter proposals and selects a design by Junkers to be developed and produced. The Huckebein comes in second place. But before long it is decided that the Huckebein is a better design, and Kurt Tank is told to plan for full production. Flight tests are scheduled for May of 1945, and 16 prototypes are to be built. Then, on April the 8th, British troops capture the Focke-Wulf facilities, ending any chance that the TA-183 Huckebein will see the prototype stage. The HES-011 engine, still delayed, never makes it into mass production. By the end of the war, only 19 engines have been built. In the months following the war, agents from Allied countries scour Europe for designs and ideas that can be used by their country's aircraft industry.
There were so many projects produced and so many projects found at various aircraft manufacturers that the Allies really didn't know what was actually worth pursuing and what wasn't. And a lot of the Allied aircraft engineers thought that some of this stuff was pie in the sky anyway, and thought that, well, you know, we know what we're doing and we're going to do it our way, which actually was not a very good idea, because the Germans were a long way advanced on their high-speed development of bombers and aeroplanes, unconventional designs.
Adolf Busemann is visited by a group of American scientists at his lab in Braunschweig, some of whom had attended the Volta Conference in 1935, but had overlooked his research then. It is only now that the Western Allies begin to see the potential of swept wings. The B-47 Stratojet, in development as a straight-winged bomber, is given swept wings when Boeing's chief aerodynamicist relays the information back to the United States. At North American Aviation, the wings of F.J. Fury fighter jet receive a 35-degree sweep before going into production as the F-86 Sabre. After the war, Hans Multop moves to the United States as part of Operation Paperclip, under which the US intelligence and military extract scientists from Nazi Germany. Working for the Martin Company, his knowledge of swept-wing designs contributes to later versions of the F-84 and the F-86 Sabre, as well as the experimental X-24 lifting bodyplane. Kurt Tank is offered a job at the Aero Technical Institute in Cordoba, Argentina, by Juan Perón's government. The ideas behind the Huckebein lift off again as he gathers a team from the Focke-Wulf Design Bureau. As the HES 011 engine is no longer in development, it is replaced with one by Rolls-Royce, the Nene 2. The fuselage is widened to accommodate this larger centrifugal engine. The wings are mounted higher up on the fuselage as compared to the Huckebein. The new aircraft is named the Heinkel He. Test flights begin on June the 16th, 1950. The plane reaches the incredible speed of 1,000 kilometers per hour. But as promising as that is, there are other problems. Pilots find the aircraft very difficult to handle, and 2 are killed during test flights. And those are not the only problems Kurt Tank faces. An economic crisis hits Argentina in 1953. The pricey Heinkel He project is halted, temporarily at first, but in 1955 Juan Perón's government falls, dealing Tank's team another blow. Soon after, the availability of cheap F-86 Sabres makes the development of a homegrown fighter a needless luxury for Argentina. It is not only the Western Allies who benefit from the work of German aviation experts. In the dwindling days of the war, Soviet forces discover the Huckebein's plans and several prototypes, which are transported back to Russia. Because of this, it is often thought that the Huckebein may have inspired the fabled MiG-15, an aircraft that rivaled the Sabre. And although the MiG-15 and the Huckebein share a number of similarities, such as swept wings, a high rate of climb, an elongated tail fin, this theory has been discredited. The majority of Focke-Wulf's engineers were taken in by the Western Allies. However, as the Soviets had possession of the German Air Ministry, the central repository for all Germany's aviation ideas, they did have all the technical data and designs dealing with swept-wing aircraft, which would have provided them the proof that swept wings were a good avenue to follow. That single B-29 landing in England set in motion events that would be felt for years to come. While it did have the intended consequences of surprising the Germans and forcing them to pour their already thin resources into the development of another new aircraft, it also laid the groundwork for swept wings to be adopted earlier than had the need for an emergency fighter not been so dire. And while the implementation of sweep theory is a boon to aviation progress, it will come back to haunt the United States in the years to come, when the MiG-15 appears in the skies over Korea.
The year is 1953. Less than a decade has passed since the Great Conflict, yet the world is once more divided, locked in a chilling, protracted struggle known only by the cold, stark designation: the Cold War. The battlefields have shifted from the trenches of Europe to the skies over Korea, and the weapon of choice is the swift, screaming phenomenon of the jet engine. For the pilots of the free world, one enemy in the sky was a persistent, terrifying question mark: the Soviet Union's most advanced interceptor, the MiG-15. The intelligence agencies of the United States had long coveted a look beneath the skin of this aerial adversary. In the quiet laboratories and design bureaus of both East and West, a remarkable shared lineage existed, a historical irony known to few. The very heart of these screaming metal birds, the powerful jet engine, traced its ancestry back to one man, the British visionary Frank Whittle. Back in the early 40s, the United States had received the fruits of Whittle's labor to propel their first jet fighters, like the Lockheed F-80 Shooting Star, designed by none other than Kelly Johnson. Simultaneously, and perhaps more controversially, the Soviet Union acquired his designs, or engines outright, from Rolls-Royce, reverse engineering them to birth their own aerial champion, the MiG-15. This story begins not with a battle, but with an act of calculated defiance and high reward. The United States Air Force issued an audacious challenge, a $100,000 bounty for the pilot who would defect and deliver a flyable MiG into their hands. On a late summer day in September of 1953, the gamble paid off. A North Korean pilot, taking a desperate chance, slipped through the enemy lines and landed his prize at Kimpo Air Base in South Korea. The capture of this aircraft, known as Project Moola, was an event of seismic importance, setting off an immediate, top-priority examination by America's greatest test pilots and engineers. From the moment the wheels touched the tarmac, the clock was ticking. Every bolt, every wire, every performance metric would be stripped bare. The findings would influence every design decision for the next generation of Western fighters. What they found, and what it revealed about the nature of Soviet aviation, is a story of technology, espionage, and the high-stakes game of the Cold War, the most important aircraft defection of the 20th century.
On 21 September 1953, the lid came off one of the most controversial subjects of recent years. It was the MiG-15, the red fighter interceptor surrounded by an aura of fact and fiction. Now we know about the MiG, what it can do and what it can't do. This is the story. The MiG landed at Kimpo Air Base at Seoul, Korea on Monday, September 21st. Its North Korean pilot collected $100,000 posted by the military for any pilot who could successfully deliver a MiG into our hands. At first, the plane was dismantled for shipment to the United States. But plans changed, and the MiG was taken to Okinawa instead. To prevent violating terms of the armistice, American officials offered to deliver it back to its rightful owners, but no takers came forward. The following Monday, at Kadena Air Force Base on Okinawa, the MiG was tugged out of the hangar ready to fly. Early in the morning, a plane load of Air Force specialists had arrived from Wright-Patterson Air Force Base to conduct flight tests on the MiG. Major General Albert Boyd, commander of the Wright Air Development Center, was one of the trio of pilots who would fly the MiG. Captain H.E. Tom Collins, also of WADC, and Major C.E. Chuck Yeager of the Flight Test Center completed the trio. Air intelligence people already knew what to put in the plane, standard JP-1 fuel. Oil was standard Air Force 1010, but the hydraulic fluid was a mixture of glycerin, castor oil, and water. In the cockpit, Russian language instrument labels were translated to English, and the pilots familiarized themselves with instrument placement. More than a score of technicians from Air Technical Intelligence Center and WADC checked over the craft prior to its initial flight. The aircraft's communist markings were changed, and every inch of the plane was inspected to make sure the MiG was structurally sound and to ensure that the plane had not been booby-trapped. From the rear, the MiG's negative wing dihedral can be seen easily. Notice the large size of the rudder. Wing fences act as flow dividers to improve low-speed handling characteristics. Since the MiG's rightful owners might demand the plane back at any time, flight testing was begun immediately. The jet assist starting unit was standard Air Force equipment, the only modification being a specially made adapter plug. Metric system calibrated instruments were replaced by standard Air Force counterparts. An accelerometer was added since the MiG had no provision for one. An external free air temperature gauge was also added for test purposes. Later, a gun camera was rigged to take pictures through the gun sight during firing passes. Preliminary engine run and taxi tests were begun on the evening of the 28th in spite of rainy weather. During these, the braking system was checked. The MiG has no steerable nose wheel, but instead depends on differential braking of the main wheels to turn. Brakes are pneumatically operated from a compressed air bottle. No compressor is carried, hence the supply of braking air is extremely limited. The compressed air is also designed as an emergency system to operate the flaps and landing gear. Captain Collins climbed into the plane the following afternoon to become the first American to fly a MiG-15. On a later flight, two F-86 chase planes started down the runway at the same time. Notice how the MiG easily outdistances them due to the MiG's low thrust loading. This factor explains the unusually good climb characteristics of the MiG. On the first flight, tests were made to determine low-altitude level flight handling characteristics at medium speeds. Functional tests were made of all systems, landing gear, controls, speed brakes, and engine, as well as handling characteristics in the landing pattern. Both in the air and on the ground, the MiG has an unusually clean appearance. Up close, it can be seen that while workmanship is good in vital skin areas, less important areas have been somewhat neglected. A coating of transparent lacquer covers the plane to reduce drag, but at the same time, MiG designers have ironically added an external antenna. The craft proved basically sound, and all systems operated properly. It handled conventionally at medium and low speeds. Approach speed on the base leg was 150 knots, final approach 120 knots, and speed at touchdown 105 knots. Landing characteristics were similar to those of the F-80. To minimize brake wear, no attempt was made to shorten landings. Much of the plane's equipment was copied from obsolescent American equipment, such as the ARN-7 radio compass receiver. The copies, however, showed good workmanship. A unique feature of the MiG-15 is its armament system. Two 23mm cannons and one 37mm cannon are positioned beneath the air intake. Both guns and ammunition are contained in a package which can be lowered by one man. This feature greatly shortens the MiG's turnaround time, since a preloaded package can be slung under a returned MiG and accurately positioned almost immediately. Fortunately, the plane was delivered to the Air Force combat loaded, so armament tests could be made. When the cannons are firing, both shell casings and ammunition links are jettisoned. Ammunition can be fired steadily for only 6 seconds, as opposed to 14 seconds with the F-86. During flight tests, several air-to-water strafing runs were made to check gun sight accuracy, as well as static firing tests into a fixed target. It is interesting to note that throughout the performance tests, data obtained compared with uncanny accuracy with information previously acquired on the MiG by Air Technical Intelligence Center. The flights made by General Boyd and Major Yeager added to the knowledge that was piling up. A series of high-altitude dives at high Mach numbers showed the MiG became difficult to control as speed increased, and at Mach .94, the aircraft became uncontrollable, pulling out only on reaching denser air. The top speed of the MiG was slightly less than the F-86 at all altitudes, although the MiG's rate of climb exceeds the F-86 at all altitudes. The MiG climbs to 45,000 feet in 9 minutes, while the F-86 takes 13 minutes. During dives, the F-86 is completely controllable at speeds which render the MiG control systems useless. During an altitude test, the MiG was climbed to 55,000 feet, while the F-86 could reach only 51,000 feet. In general, MiG handling characteristics at all speeds are not so good as the F-86 because of the MiG's small aileron surface and lack of elevator effectiveness. The MiG is most effective as a combat fighter at lower speeds, where its lower thrust loading allows greater maneuverability. Pilot protection on the MiG consists of an armor-plated ejection seat back of adequate thickness and the usual bulletproof glass. Fuel tanks, located in the fuselage, were not self-sealing. Oxygen and cabin temperature systems require constant pilot attention, as did most of the equipment in the plane. Pilots reported cabin temperatures as high as 42 degrees centigrade at low altitudes and below freezing temperatures at high altitudes. These extremes in working environments would seriously limit a MiG pilot's performance. At the conclusion of the tests, the tally sheet read like this. Desirable features of the MiG. 1. Ability of the MiG to operate over 50,000 feet. 2. High rate of climb. 3. Rapid acceleration from low speeds. 4. Short turning radius. 5. Short takeoff and landing distance. On the undesirable side of the score sheet are these. 1. Loss of aircraft control at high Mach numbers. 2. Loss of pilot vision due to inadequate defrosting and poor rearward visibility. 3. Poor lateral directional stability at high altitudes. 4. Slow rate of roll. 5. Equipment requires constant pilot attention. Compared with the F-86, the MiG is an inferior though still formidable weapon. The 13-to-1 kill ratio of F-86s over MiGs can be attributed directly to superior planes and better trained pilots. 4 days and 11 flights after the test program started, the MiG had no secrets left.
In 1951, a Mikhail Goryevich MiG-15 is shot down over Korea's west coast and plummets into the Yellow Sea. The jet is pulled from the shallow water by US and South Korean forces, transported by a British frigate for study. At a US Air Force base in Dayton, Ohio, the plane is pored over. One of the first discoveries of this incredible aircraft comes when the engine is inspected. Expecting to find a hybrid of Russian and German jet technology, the team studying the captured prize receive a shock. The plane is powered by what appears to be a Rolls-Royce Nene 2, designed in England. 1940. Since the signing of the Molotov-Ribbentrop Pact, Germany and the Soviet Union have been in an alliance, using their combined might to carve up Eastern Europe. With France giving in quickly to the Nazis, England's newly appointed Prime Minister, Winston Churchill, knows that German troops will soon be clambering up the English beachfront. He decides to send a new ambassador to Moscow, and a member of Parliament volunteers for the job. He is Richard Stafford Cripps. Born into privilege, Cripps' first love is chemistry, and following a stint as an ambulance driver during the Great War, he studies law and becomes a successful attorney before an interest in politics lures him to run for office. Cripps joins the Labour Party and in 1930 becomes Solicitor General in Ramsay MacDonald's government, a position that includes the honour of becoming a knight. Though regarded by all as a brilliant man, Sir Stafford Cripps has a tendency to ruffle feathers, and soon finds himself clashing with Labour over his political leanings. Some of his views are considered so extremely left-wing by the Labour Party that he's chased out. Now sitting as an independent, he finds himself on a trip to Moscow, with a goal of aligning the Soviet Union with Britain.
Stafford Cripps was certainly born into a life of privilege, and his father was a Conservative MP. This no doubt stimulated his own interest in politics. But what I think really led him into his own particular line in politics was really his religion. We can't understand Stafford Cripps unless we understand that he was a committed Christian who had very fervent beliefs. In some ways they seem rather naive. They're certainly idealistic. He believed in the brotherhood of man. The crucial event for him was really the economic crisis of 1931, when Britain was hit by the so-called economic blizzard that swept away the Labour government and seemed to indicate that the capitalist system simply wasn't coping and couldn't cope. This led Cripps from being a moderate member of the Labour Party into adopting Marxism, which naturally involved a degree of sympathy with the Soviet Union.
In 1940, while the Battle of Britain rages, Cripps arrives in Moscow. While hope is high that he can steer Russia into an alliance with England, early results are not at all promising. Just days after Cripps has a 3-hour meeting with Joseph Stalin, the Soviet Premier and Foreign Commissar Vyacheslav Molotov gives a speech on how successful the Russian-German alliance has been for the country. Cripps continually warns Stalin not to trust Hitler, but to no avail.
The key episode was really from 1940 to 1941, when he went to Russia as Britain's ambassador. And what he found there certainly changed his view and formed what to many people will seem a surprisingly unfavourable view of Soviet Russia for such a left-wing figure.
From his book, The Cripps Version, Dr. Peter Clark reads Cripps' correspondence with his daughter during the politician's time as ambassador in Russia.
He's talking about the regime and says that it has many difficulties, perhaps due partly because they're inherent in every form of dictatorship. And he continues in this way: if to all these difficulties you add the government by secret police and spies, which is the only method for a dictatorship, then in such a country as this, with a people of this kind apt to intrigue and brought up in underground revolutionary activities, you get perpetual change of personnel and liquidation of many of the more intelligent people, creating new difficulties of organisation. In the passage I just quoted, we see already, surely, that Cripps accepts that this is essentially a dictatorship, it is essentially a police state, that it is in many ways a deeply unattractive society. During the war, admittedly, he argued very strongly in favour of alliance with Russia as the best way to beat Hitler's Germany. But long before the end of the war, he was certainly no ideological captive of the communist system.
Within a year, Cripps' warnings about Hitler's trustworthiness become all too real, and Stalin must face the awful truth. Operation Barbarossa begins, as Nazi Germany storms into Soviet-controlled territory and pushes Stalin's forces back. It's a swift, fiery onslaught that knocks the Red Army back on its heels. It's a turn of events which suits Winston Churchill just fine. Not only does this new Eastern Front relieve some of the pressure on his troops, but it gives him, and particularly Cripps, clout with Stalin and amongst the Russians. A bond is forged over their common enemy, and soon an Anglo-Russian alliance is formed. But Churchill may be on shaky ground at home. Not only do the Russian politicians embrace Cripps, but the British public do as well. After a broadcast to the nation on the situation in Russia, Cripps is suddenly one of the most popular men in the nation, even seen as a contender for the position of Prime Minister. At a time when defeats are plentiful, Cripps makes it known that he'd be ready to take up the post if Churchill is unable to manage. Churchill seizes on this. In March of 1942, he sends his new rival to India in order to broker a deal with Gandhi and Jinnah. If the Cripps mission is a success, India will aid the war effort against the Nazis in exchange for self-rule once the conflict is at an end. But the mixed messages Cripps seems to be giving to the Indian negotiators during the trip causes it to end with no deal in place. The Indian Congress Party will not agree to aid England in the war. But aid is coming from another source. Through its Lend-Lease program, the United States of America begins to send supplies to the Allied forces in exchange for gold. They supply vast numbers of vehicles throughout the war, and Britain is the main beneficiary of the deal. The Soviet Union is far behind the West in technological advances, and needs aid as well. Russia receives close to 15,000 aircraft by the war's end, almost 20% of all the aircraft that they use. The most prominent of these is the Bell P-39 Aerocobra. It's best suited for low-altitude flight due to its lack of turbo superchargers. Its unconventional layout, with the engine behind the pilot, leaves little room for storing fuel. The standard load is carried in the P-39's wings. It's therefore limited to short-range tactical strikes. The most advanced fighters and bombers the Americans keep for themselves. It aggravates the Soviets to be given the older technology, but they make do with what they're given. Of the equipment delivered, much of it is not suited to combat on the Eastern Front. Aircraft meant for tropical conditions are now used in a much colder climate. There are few spare parts, and so crews must sometimes improvise as best they can. The Soviets learned to adapt the Western technology to their needs and uses, skills that will serve them well in the years to come. 1945. First, Nazi Germany falls, and then so does Winston Churchill. The general election on July the 5th knocks the Conservatives from power and brings in a new Labour government, led by the wartime coalition government's Deputy Prime Minister, Clement Attlee. The public feels that the Labour Party will be more adept at helping England rebuild in the post-war period. Joining Attlee's cabinet as Minister of the Board of Trade is Sir Stafford Cripps.
The election of a Labour government in 1945 came as a great surprise to the world, who imagined that Winston Churchill would inevitably win re-election, having won the war. I think it's important to realise the strong elements of continuity, especially in foreign policy, that went over from Churchill's coalition wartime government, in which Labour had played a big part, into the post-war Labour government.
The main thrust of this new government is to rebuild the war-weathered country. It's about winning the peace by giving Britons a crutch to lean on. They use the 1942 Beveridge Report as a guide for reforming the country. Attlee brings about sweeping changes that will alter the country for decades to come. Free national health care, education for everyone up to the age of 15, social security. He works towards giving India and Burma their freedom. It's far removed from the direction that their ally America is heading. More and more nations adopt communism, and never comfortable with these ideals, America finds these new social developments within Britain curious and worrisome. Churchill was the sort of man Americans understood, and Attlee is no Churchill. He's small and modest, spares his words when they aren't needed. To Americans, the contrast is a sharp one that gives them pause. Labour's domestic policies seem much closer to communism than to capitalism.
Foreign policy was largely in the hands of the Prime Minister Clement Attlee and the very strong Foreign Secretary Ernest Bevin. Now, both of them, in 1945 and 1946, were ready to take a much stronger line against the Soviet Union and its threat to the integrity of states in Eastern Europe than the Americans were at the time. So Attlee and Bevin had to argue with President Truman about the need to stand up to Soviet Russia. It wasn't really until events took their own course during 1946 that, in a sense, Truman came round to the rather harder line that the British government was already following. It's therefore somewhat surprising to find that in popular politics in the United States, Britain, simply because it had a Labour government, was then perceived as a weak link in the Western alliance. If you come down to the realities of the situation, you see that it's in fact British policy that is actually more consistent through the 1940s in taking a firm line in opposing Soviet expansionism. And Cripps, for all his previous sympathy with the Soviet Union, is firmly in support of the line of the government of which he's a leading member.
America's astounding capacity for production kept Britain well supplied during its darkest days following the Battle of Britain and supplemented their renewed manufacturing throughout the rest of the war. And now, very suddenly, the Lend-Lease program, that boon to Allied nations throughout the war, ends. America turns off the tap and stops the flow of resources into Britain. Not only that, they send the bill. Over £1 billion to be paid back over a 50-year period. As America is entering a post-war boom in prosperity, Britain is withering under its immense debt and damaged infrastructure. 750,000 homes damaged or destroyed. 1/3 of gold reserves spent. Food rationing becomes more stringent than it had been during the war. Coal, an absolute necessity for providing Britain with heat and manufacturing, is scarce.
We shall only get it right if we can produce much more than we did before the war. That's the only way we can get the things we need. Food, clothes, entertainment. A little less struggle to live. A decent home and warmth. We want colour in our lives. A better education for the kids, bigger pensions for the old people, and all the rest. No doubt we're in a bit of a tough spot, and it'll take a year or two to get out. But we've done it before, and we can do it again.
And while the post-war situation is tumultuous for the common people, it's a windfall for the Allied militaries. Germany's defeat sees its treasure trove of technological secrets scatter for anyone looking to pick up the pieces. The Allied nations rush into German territory to recruit the top scientists and to integrate these advancements into their own country's technology. Russian forces lay their hands on the Reich Air Ministry in Berlin and the many secrets within it. Swept wings, rocket power, and the jet engine. With this information, they can make a vast leap ahead and finally begin to catch up to the Western powers. And since the pre-war days, when Stalin assessed his nation to be 50 to 100 years behind Western technology, the Soviet Union has been making great advancements. One Soviet manufacturer, the Mikoyan Guryevich Design Bureau, has been creating aircraft since 1940, establishing a solid reputation for creating fighter planes. Their first post-war design, the MiG-9, is powered by a copy of the captured German BMW 003 engine. As early jets go, it has a fairly conventional design, an all-metal fuselage with straight wings. For their second-generation jet aircraft, they'll be incorporating some new ideas in aerodynamics. But for all the advancements that they'd like to implement, the power plant is not up to snuff. The German jet engine that the Russians discover has its flaws. The axial flow system, while powerful, is difficult to maintain. Engines quickly burn out and must be replaced. Their short lifespans plagued German ground crews throughout the war, and though the Soviets pursue the creation of their own jet engine based on this technology, they find themselves facing the very same problems the Germans had. Germany's most advanced jet engine design is proving difficult to perfect. The new airframe designs that Mikhail Gorgievich are creating will need something more advanced and reliable than the adapted German engine. To keep up with Western development, Russia will need a centrifugal flow jet engine, like Frank Whittle has developed in England. While not as powerful as the axial engine, it's reliable and has been a proven performer. Rolls-Royce has continued to make developments using Whittle's ideas, and currently have the Neen 2 engine, which, despite its great power, has only thus far been used in prototypes of the Hawker Seahawk and the failed Supermarine Attacker. Without an advanced jet engine, Russia's aircraft development will be at a standstill. The Soviet aviation minister Mikhail Khrushchev and designer Alexander Yakovlev suggest to Stalin that they purchase more advanced engines from another country. Stalin scoffs at Khrushchev's idea. What fool will sell us his secrets, he asks. Despite knowing that his men will fail on their journey to purchase this technology, Stalin allows the trade mission to go ahead. MiG's Artem Mikoyan, engine designer Vladimir Klimov and others travel to England to tour Rolls-Royce's plant and to see other British aircraft developments. When the trade mission lands in London, they find a socialist government ready to embrace them. There's still much goodwill afforded to Russia, still seen by British eyes as an ally in the noble war against Nazi forces. That, and post-war England needs money. The Soviet delegation tours the Rolls-Royce plant and are shown their latest engine developments, the Derwent and the Neen. They ask to purchase several of each. When the order comes across the desk of a Ministry of Supply employee, he warns Minister John Wilmot against selling the Soviets the technology. Britain is the absolute leader in jet engines. Russia is at least 5 years away from similar developments. Selling them one of the nation's greatest achievements would be, as Stalin has said, foolish. But the sale is pushed through by the President of the Board of Trade, Sir Stafford Cripps.
I think it was a socialist move to a socialist government, or an extreme Soviet government. We'd helped the Soviets before, or the Stalinists before, of course, at the beginning of World War II. But here I think this was going beyond the call of duty after the end of the war. And it certainly hurled them straight into the Premier League in aviation.
Despite a distrust of Stalin after his time in Moscow, Cripps sees the world breaking into two spheres of influence and wants to bring those sides together. Not only that, the sale means a good deal of money for Rolls-Royce at a time when big contracts are hard to come by. Cripps even offers to allow the Soviets to build the engine themselves under license.
The circumstances of the sale of the Rolls-Royce engines to Russia can't be divorced from Britain's economic predicament after the war, with a desperate need to increase exports. Cripps, as President of the Board of Trade, was the minister with primary responsibility for British trade. It's only natural, therefore, that he should have wanted to encourage expansion of British trade and opportunities for British exports in every direction possible. And certainly in 1946, he was taking the view that Russia was a promising export market as far as British manufacturers were concerned. I think it's only natural, given all the circumstances, that he would have wanted to approve the sale of aircraft engines, which, after all, at that time, were not regarded as classified or restricted, had not been put under any sort of military ban. And there's frankly no need to seek further for an ideological explanation of his decision to approve a deal that he saw simply as being in the British national interest in order to revive British trade.
While Cripps' actions on the sale may have been honest, The Soviet delegations are less so. Rather than accepting the license, the Russian engine manufacturer Klimov begins to reverse engineer the Neen from the examples they've purchased. The Russians begin producing a version, the Klimov RD-45. But creating a successful engine is proving difficult. England has a long history of metallurgy dating back centuries. Small forges all over the British Isles have developed techniques to create strong metals from ores and minerals found throughout the empire that are perfect at handling the high stresses and heat associated with the power of a jet engine. Russian metallurgy is not nearly as advanced, and they find this one of their main stumbling blocks in duplicating the engine. The Neen can run 500 hours between overhauls, but the Klimov copy doesn't last more than 100. They increase the size of the combustion chambers and turbine and refine the alloys used to create the engine. This new model is known as the Klimov VK1. With the engine ready, they can now finalize designs. In April of 1947, the Council of Ministers issue a decree ordering Mikhail Gorbachev to build 2 prototypes of a new jet fighter, one that will put the Soviet Union ahead of the field in aircraft design. The Boeing B-29 has been America's frontline bomber since the final year of World War II. It's a revolutionary leap ahead of other aircraft, with its pressurized cabin and computer-assisted gun turrets. And now that the United States has the atomic bomb, the Soviet Union needs the future capabilities to defend against a bomber entering their territory with one of these tremendous weapons. The Council of Ministers want an interceptor for just such a situation. Mikhail Gorbachev looks back at their earlier aircraft to see any lessons they can learn. Their experimental canard plane, the MiG-8, had swept wings, a feature that they're interested in exploring further. Some captured German designs, like the TA-183 Huckebein, had swept wings implemented as well. Their latest jet, the MiG-9, has been promising, and they used this as the base to build from. Its engine troubles have been solved with the Klimov engine in place of the BMW power plant. It will also receive newly designed wings, swept back at an angle of 35 degrees. After some additional refinements, this new creation, the MiG-15, has a top speed of over 650 miles per hour. Though early production aircraft have a tendency to roll, these problems are lessened by adding aerodynamic trimmers near the ailerons and rudder. It's also recommended that pilots stay below Mach 0.9 to lessen any other stability problems. Test combat trials are conducted with a captured B-29 as well as the Soviet copy, the Tu-4. To shoot down the Superfortress, the MiG-15 is armed with 2 23mm cannons and a single 37mm cannon. In 1949, production stops on the MiG-9 and the MiG-15 enters the Soviet Air Force. June the 25th, 1950. North Korean troops cross the 38th parallel into South Korean territory. By July the 5th, American forces have joined with the South Korean army. The United Nations also enters the fray under the guise of a police action. Soon, the conflict escalates beyond a ground war when the US calls for strategic bombing with its B-29s. In addition, piston-engine fighters like the Mustang and the Corsair, left over from the Second World War, are joined by the jet-powered Gloster Meteor and the F-80 Shooting Star. With the South Korean forces bolstered by UN support, North Korea also looks outside its borders for help. In October, Chairman Mao Zedong of China, fearing that a US occupation of the Korean peninsula would eventually lead to war with his country, sends a volunteer army into the fray. The North Korean and Chinese leaders ask Stalin for help. And while the Soviet dictator is unwilling to send in ground forces, he does provide aircraft in the form of the MiG-15 jet fighters, painted in Chinese colors to mask Soviet involvement. Soviet pilots are sent to train North Korean and Chinese airmen how to fly the fighter jets. They're taught simple Chinese phrases and dressed in Chinese uniforms and sent into the skies to combat and shoot down B-29s and engage the UN fighter forces. The piston-engine planes like the Mustang and the first-generation straight-winged jets are no match for the abilities of the MiG-15. It's faster, can fly higher and longer than any of its opponents. The Soviet victories come fast and often. The American pilots use their years of dogfighting experience to counter the superior technology at their enemy's disposal, but it's not always enough. Soon, B-29s are forced to limit their bombing runs to nighttime.
The first sighting of the MiG-15 in the Korean War, I think, had the same impact on pilots that as did the first sighting of the Focke-Wulf 190 just after the Battle of Britain, when it appeared in Europe. And we had nothing really to compare with it for the next year. Its success was due to two factors. One was the jet engine they had, the NIN, and the second one was, of course, the data they got from the captured German sources on the sweepback, wing sweepback. So it was a twin contribution, if you like.
Soviet air superiority begins to change in December of 1950, with the arrival of an all-new fighter aircraft for the American forces, the F-86 Sabre. First developed as the straight-winged FJ Fury jet, its design has changed to incorporate 35-degree swept-back wings and automatic slats. The Sabre is not a leap ahead of the Soviet jet, but it does level the playing field. The discovery of an advanced British engine in the fuselage of a Russian-designed plane infuriates the Americans. This is not the first time the Soviets have made a huge leap ahead in military technology. The August 1949 detonation of Russia's first atomic bomb showed just how far they could advance technologically in a few years, with some outside help. First, Klaus Fuchs, a German-born scientist brought in by England to work on the Manhattan Project, has been arrested for providing the Soviet Union with atomic bomb designs. And at the moment, Donald Maclean, a high-ranking British Foreign Ministry official, is suspected by the FBI of providing the Soviets with a variety of information. As the British representative on the American, Canadian and British Atomic Secrets Council during the war, he's had access to nuclear secrets at a time when the quest for the bomb was known only to a few. It's in the autumn that UN forces finally get their hands on the MiG-15 and discover the secret of its power plant. It's confirmed when two men are dropped behind enemy lines to a crashed MiG-15 dug into the ground. No chance to remove the entire wreck, they use grenades to separate the engine. The Americans are livid. How could England have handed over a piece of powerful technology to Stalin's regime? But they have little time to blame Sir Stafford Cripps for selling the engines to their enemies. He's been retired for close to a year due to failing health. In October, Winston Churchill's Conservatives edge out the Labour Party, knocking Attlee out of government. Churchill, as Prime Minister once more, makes Anglo-American relations a priority again. And with him back in power, there's little chance that the Soviets will find any socialists to sell them other technology. In the northwest of Korea, in an area along the Yalu River, the first large-scale jet versus jet air battles of history take place, in an area dubbed MiG Alley. When the Sabres reach MiG Alley, they have only 20 minutes of fuel to engage the enemy with. The MiG-15s, with their bases nearby, can linger much longer. American pilots charge in at 40,000 feet, only to find the MiG-15s flying 10,000 feet above them. The MiGs hide in the sun's glare, then swoop in as a formation of Sabres are on patrol. The Russian fighter does have its share of weaknesses. The cannons it's equipped with, while powerful, have a low rate of fire compared to the Sabre's guns. It also has poor stalling characteristics. A Sabre pilot can force a MiG-15 into a dive that becomes a spin that cannot be recovered from. The combat experience of the United Nations pilots ultimately trumps the sophistication of the Soviet plane. By war's end, the UN forces have shot down 900 enemy aircraft, almost 800 of which are MiG-15s. But the aircraft has proven that the Soviets can use a blend of ingenuity and craftiness to match the West's innovation. Between the USSR, Czechoslovakia, Poland and China, over 16,000 MiG-15s are produced. In 1958, Rolls-Royce Deputy Chairman Whitney Straight is touring a factory in China when he sees an engine curiously similar to the Nien. Discovering that its origins lie in the reverse engineering of the Nien, he attempts to collect payment for the almost 50,000 engines that Klimov made by taking and adapting the design and licensing it to other countries for the MiG-15 and later aircraft. £200 million is the compensation he's looking for. He leaves without one farthing. The man whose decision led to the jet engine being copied is long since gone. Sir Stafford Cripps dies in April of 1952 in the midst of the Korean War. And while he's remembered mainly for his contributions to Britain's war effort and the post-war cultural shift, he will forever be tied to the MiG-15 by that one decision.
Cripps has always been, to a large extent, the prisoner of his own reputation, but it was a reputation that shifted over time. In the 1930s, his own high principles led him to take a very extreme political position on the far left of the political spectrum, arguing that only full-blooded socialism or even communism could offer an answer to the economic problems of the day. By the 1940s, Cripps's position is quite different from what it had been 10 years previously. It took people, quite naturally, some time to catch up with the rather rapid evolution through which he'd gone.
An evolution which is often overshadowed in aviation circles by this gift to Russia. A decision that may have been motivated by all the right reasons, but strengthens the might of the Soviet military for years to come.